Okay, hi, my name is Kayla. I am at UCF with Dr. Addie Dove, and my question is primarily for Dr. Schmidt. I'm wondering, with your experience on Apollo 17, and for example, it was very cool that you were able to say, when I took this picture so we could see XYZ thing. I'm wondering, between that and then working for so many years with the data from that and other experiments, if you have any advice looking forward to the future missions, so Artemis and beyond, what can we do to put ourselves in the best position to have the best science and exploration we possibly can have?
Well, at the most detailed side of answer to your question, Noah Petro's already asked me, what would I recommend relative to this, to what I just said in my abstract, relative to Artemis 3, and find some boulders that leave tracks so you can date them and sample them like we sampled almost inadvertently, but a really great suite of samples at Station 6, which led to being able to actually determine the rate of maturation of these two components, the alpha particles and the protons. And now long term, you need to have a sampling plan executed so somebody downstream can do a complete synthesis of the landing site. We tend to make proposals for a very narrow scientific objective. We've got to fund, eventually, once you get all that data, somebody has to pull it together and synthesize it, and it's amazing the things that are going to come out of that. I just can't recommend that more, is to ultimately you have to synthesize all the data, and that should be done for the other Apollo missions. It really should. I'm not going to have time to do it. But really, the other missions have, particularly the J missions, the last three, the other two of the J missions have, I think, a tremendous opportunity to dig into those sites and either verify or contradict or show trends relative to what I've been able to do at Apollo 17.
That's amazing. Thank you so much.
So, come on up.
Hi, I'm Angela from NCU in Taiwan, and I have a couple of questions for Zabo. Yeah. So my first question is that did you include the iron core in your hybrid simulation?
We did some with or without. I think for the steady solar wind that we look at, the iron core is not as important. If you go more for extreme solar events of CME impacts, then you need to include it. That was more my finding, or our finding there.
And what would be the conclusion of your results under extreme solar wind conditions, for example, CME or something? And to my understanding that in the SD train code, that the incident angle may be matter, but under extreme solar wind condition, does that matter also?
The angular dependence, it gets a little bit smeared out because you have a rough regolith. But the conclusion, they didn't have the space to put it in there. But basically, under the very most extreme solar storms that have been observed at Mercury, you should get enough sputtering to overcome the micrometeoroid composite or component that we see all the time. But it's probably very much the strongest CMEs. So it should be observable, but not that often.
But does the sputtering yield change?
I mean, the sputtering yield doesn't change that much, but the number of ions that hit the surface changes by orders of magnitude because the magnetosphere gets compressed even down to the surface in the strongest cases.
Let me just make a quick comment on that. In this course of this synthesis, I've developed what is maybe a little bit more than a gut feeling that the most important solar wind exposure on the moon is from the 1 gigawatt plus events, the big ones, and that the 4.5 megawatt steady solar wind doesn't have nearly the effect that occasional major events have. I think it's really I haven't been able to prove that yet with the data that I put together, but my gut is starting to say those are the most important things that happen on the moon.
I'm going to take the chair's prerogative here and inject a little bit. So, in all of these models, though, on the moon, photon-stimulated desorption is also important for removal, competitive with sputtering. Is that not the case?
I mean, if like for sodium, this comparison would look very different. I think for sodium, where you have such high photon-stimulated desorption or thermal desorption yields, it will be difficult to get to the same rates. But for calcium and magnesium, where you have the lower source rates, essentially mostly through micrometeor sputtering, I think then you can get sputtering to be more important.
I see. Okay. Actually, we have a question online. Rosemary, you want to ask your question?
Yes, I also have a question for Paul Szabo. Since the moon is open to the solar wind and Mercury has, obviously a magnetic field, I was wondering, your increase in the sputter rate relative to micrometeoroid impact, how does that affect the scale heights of especially calcium and magnesium? And I mean, as you know, the scale height for magnesium at Mercury is consistent with impact vaporization, and for calcium, it's much more energetic. And I was wondering what you would predict for the moon.
I mean, obviously you will have very high scale heights. I think at the moon, because it's smaller and the higher binding energies play a role, I think a lot of them would actually escape of the sputtered particles. But the part on the CME impacts, or also the energetics part, that's still ongoing. So I can only say some vague things there. But at Mercury specifically, you will get a strong exosphere component over the day side. That's a difference there.
So you would maybe look at the tail for the highly energetic part.
Potentially, but I have to look a little bit more into that. But thanks for the question.
One thing to remember is that prior to about 3.60 billion years ago, and this is out of the synthesis again, the moon's magnetic field was deflecting the solar wind. And there's good evidence in a number of ways in the synthesis that indeed the only maturation source were uranium thorium derived alpha particles and betas. So just keep that in the back of your mind, that the moon was much like Mercury, more like Mercury before 3.6 billion years ago. We get that from the pyroclastic ash stuff. Strata at Shorty Crater.
Sorry, I have the last question still for Szabo. Yeah, so I think you use the calcium and magnesium for the tracer for the two high energy pathway, and I think it works well with Mercury because we can see the asymmetry and the seasonal variation on Mercury, right? But how reliable is that diagnostic on Moon? Or is there any other way to verify this?
I mean, for calcium and magnesium specifically through messenger, I would say we have better data at Mercury. That's why I'm doing this comparison. There are upper limits for elements like calcium, but for the spatial distribution in the exosphere, the data from Mercury is nicer for that.
So we have time for one more question. Jeff was up first here. Brian, I'll buy you a beer later.
Jeff Gillis from Washington University. I have a question for Elena. Can you discuss a little bit the statistics that you used for the different red spots? As far as you showed a box, I was just wondering, did you just average that box, or did you somehow use geology to pick smaller regions of interest to do the statistics?
Yeah, so I mean, I tried to select regions that were only red spots, so I based that off of Diviner as well as like just topography of the region to select the boxes originally, but then the spectra is an average of the boxed area across all the wave bins.
Okay, let's thank all of the speakers for a fantastic session here.